Hello, everyone. Can you hear my voice?
Yes, sir.
Okay. So we will be starting with the session in a moment. This is the first session on INMO geometry. And what did you learn yesterday in the previous yesterday's session from Anushka? I think Anushka took that session, right? So can you tell me what you
Also, problems on algebra.
problems from algebra? Okay. So that is good. Let's wait a few minutes for others to join, and then we can start our journey in geometry. Uh, so, those who are joining right now, this is the second session of INMO Cheenta INMO Geometry Camp. The INMO is coming up pretty shortly, I think in 2 weeks, less than 2 weeks. So, yeah. Okay, so let's start, and then we can sort of um, let's see. Yeah. So after we begin, we can gradually let others in on this particular session. I'm not sure how to do that though. Okay. So the thing about this particular session, and I'll take I think two more on geometry if I have this right schedule, is that we will be interested in a review of some of the ideas, and we will also go into learning a few new things which we can directly use in geometry. So today we'll start with a very simple technique of the invisible point. It's a very standard tool in geometry, the invisible point tool. And before we do that, let's start with two simple but powerful tools in circle geometry: the tangent radius property. So maybe you already know this. And the other one is the tangent chord property. Tangent chord property. So I'm sure most of you know this because you already qualified. Maybe you qualified for IOQM. If you do not know this, this is the gist of it. The first one, that is the tangent radius property, is this: that if you have a circle and if you have a tangent to the circle at a certain point, let's say this point is P and the center of the circle is O, then if you join OP, this is the radius, this is the tangent, then the radius is perpendicular to the tangent. Simple stuff. Maybe you already know this. And one of the reasons I love this problem is you look at the notion of perpendicularity from a metric point of view. What do I mean by a metric point of view? Metric means distance. So the interpretation that the perpendicular is the shortest path will be heavily used here. So This is usually not present in angle chasing sort of geometry problems where you are just manipulating with angles. Here we strongly use the notion that perpendicular path is the shortest path from a point to a line outside the point. And the proof relies on that because you say, okay, if you take any other point, you can draw one perpendicular from O to the tangent line. If you take any other point Q as the feet of the perpendicular, you can easily show that OQ is larger than OP. So in fact, OP turns out to be the shortest path from O to the tangent line, making it the perpendicular. So this is well known. The other property that is often more useful is the tangent chord property. So I'll spend a minute on that. This property is like this. You have this tangent line like this. Let's call this the tangent line. And the point of tangency. Okay, someone else is joining. Who is joining? Okay. 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 This is very weird. Uh, let's go ahead, reset. Okay. Let's add that person. Okay. All right. So, yeah. No, it's fine. So we have the tangent, and suppose we draw a chord. Let's call this point A. Let's draw a chord AB. So starting at the point of tangency, let's mark another point X on the tangent just for reference. Then the property says that the angle BAX, which I remember as chord to tangent angle, this angle BAX is equal to the angle subtended by this particular chord in the alternate segment. So it's like this. So subtended means this particular angle sits on this particular chord and the point is on the circumference of the circle. And the word alternate means it sort of is not in this particular part of the circumference, it's in the other part, the part that is not with the first angle. So these two angles are equal. I will not go into the proof of this because this is, I mean, for INMO this should be elementary. So these are two things. Assume that you should know this. And let's talk about the invisible point property that we can use with these two methods, with these two theorems. So here is a problem. Suppose we have a right angle. Suppose we have a triangle, any triangle, not right angle necessarily. In fact, let's start with, so here, let's go to a new board. So here is a problem. Let's start with an acute angle triangle ABC. So here we go, ABC, an acute angle triangle. And the circumcenter is O. Circumcenter is O. So I'm just assuming that you guys know about circumcenters. Again, this is just the training camp. It's not the main geometry module, so I cannot discuss all of those details here. I'm assuming that you guys already know about circumcenter and the proof of it. So ABC, O is the circumcenter of it. And we have a point M, which is like this. So M is a bit clever. It's like this. You draw, okay, I'll draw M like, maybe I'll just make it a little bit more here. So M is here, suppose. So MA is tangent to the circle. MA is tangent to gamma. So this circle is gamma. MA is tangent to gamma. Okay. And this is the number one data. The other data is, and MCB is 90 degree. MCB is 90 degree. Okay, so what you want to do is you want to draw a line that is parallel to AB, parallel to AB. So let's call this T. MT is drawn parallel to AB. These three things are our given information, and we want to show that AOT are collinear. AOT is collinear, or are collinear rather. Okay, this is the goal. Now I'm sure maybe some of you have heard about the Shiva's theorem, the Menelaus theorem, all those things.
Sir, is this invisible point thing like phantom point?
Indeed, they sometimes call it the phantom point. Yes, it does. It's similar. It's actually probably the same thing. Yes. So okay, so I'm assuming that you have heard about Shiva's theorem, Menelaus theorem, for proving collinearity and concurrency and stuff like that. I will be discussing them in the next session. But in today's session, we will not use those things. Just to make sure you understand that we are not interested just in this problem. We are interested in the technique that will be used in this problem, because that will be useful in other problems as well. Okay, so how do I use the invisible point technique? What I do is I'll be just joining AO and creating a point T prime, which I will call the invisible point, because of course T prime was not there up to this time. So this point T prime is now here. I will be showing that T and T prime are the same point. T is equal to T prime. If I can show that T is equal to T prime, then my job would be done, right? Or the length TT prime is 0. That is, sometimes we can say it like that. So how are you going to show that? Okay, what you do is you join MT prime, and show that MT prime is parallel to AB. This is the strategy. Join MT prime, and then show that MT prime is parallel to AB. But MT was parallel to AB. That means that MT and MT prime are the same straight line by Playfair's axiom. So I must point out the Playfair's axiom here. It's very, very fundamental to the Euclidean geometry. The Playfair's axiom says, one of the 5 Euclidean axioms, is that if you have a line L, and if you have a point P outside that line, then it's possible to draw only one line parallel to L through P. Now, for thousands of years, people believed that Playfair's axiom can be deduced from other axioms of Euclid, but turns out they are really independent. and if you do not accept Playfair's axiom, you get other types of geometry like non-Euclidean geometry, hyperbolic geometry, and stuff like that. So I'm not going to go into that, but I'm going to tell you how we are actually utilizing Playfair's axiom here. If we can show that MT prime is parallel to AB, earlier we knew that MT is parallel to AB, then by Playfair's axiom, only one line is possible through M that is parallel to AB. By virtue of that, MT is equal to MT prime. You understand this particular theorem will probably not be true in a non-Euclidean context. For example, if it is a hyperbolic geometry, then it's probably not going to be true because this strategy wouldn't work. I'm not saying the theorem wouldn't be true, but this strategy wouldn't work because in hyperbolic geometry, through one point you can have multiple points, multiple lines parallel to a line. So anyway, can anyone show by simple angle chasing that indeed MT prime is parallel to AB? Show that MT.
Yes.
Okay, I'll just give you a little bit time to everyone to think. Why don't you write down your in your notebook? You can draw the picture, and then we can discuss a little bit after.
Sir, it's just 3 steps of angle chasing.
3 steps of angle chasing. Okay, Arjun is actually right. Yes. Use the stuff that we already talked about. Use the stuff that we already talked about.
Sir, will we also be doing like a higher theorems? Like by higher theorems, I mean very tougher problems, etc. Well, more tougher problems.
Yeah, I'm sure we will be doing that.
So done.
Okay, someone else has done. Who has done? This is Ryan. Okay, I see. So two persons have already done it.
I have finished it also.
Okay, you did it already. Okay, that's good. So okay, Arjun, go ahead. You tell me what you have in mind?
Sir, the main thing is that angle MCT dash is equal to angle MCB equal to 90 degree.
Okay, so
And the previous property you told, we know that OAM is also 90 degree. So this shows that the sum of opposite angles of quadrilateral AT dash CM is 180 degree, which means that this quadrilateral must be cyclic. Uh, like these 4 points lie on some circle.
so you are saying that an AMCT prime is cyclic.
Yeah.
Is that what you're saying? Okay. So that's because this angle is 90 and this angle is 90 because OA is perpendicular to MA because radius is perpendicular to tangent. Okay, yeah, of course. So sum of the opposite angles is equal to 180 degree, and yeah, okay. So this is a cyclic quadrilateral. Fine.
After that, we can again use the property you previously told, like by alternate segment theorem, which we usually call it angle ABC is equal to angle MAC.
Angle ABC. Okay, so this angle right here, which is subtended by the chord AC, is equal to this angle MAC. Okay, that's right. Because of
And
the alternate
since
segment theorem. Yeah.
this quadrilateral AMCT dash was cyclic, so we also know that angle MAC is equal to angle MT dash C.
Okay, so this angle right here is also equal to angle MT dashed C because this is a cyclic quadrilateral, and this two angles are subtended by the same chord MC. So MC is the chord that is
Um,
subtending
yeah.
both of these angles.
So after that, we know that angle ABC is equal to angle MT dash MT prime C. So this means that that MT prime is parallel to AB, and so we are done by phantom point, or say the assume you told, that Playfair's assume.
Okay, yeah. So we showed
The
that ABC and M.
key thing we need to also know that is, like, the line through M which will be parallel to AB will cut line BC in at most one point. So that's one thing to note. It cannot cut in 2 points.
Line through from M to B. Sorry, can you say that one more time?
Like the line passing through M parallel to AB can cut line BC in at most one point. So T and T dash cannot be two distinct points. They must be the same thing.
Yeah, I mean, if yeah, of course. So if they are both parallel to AB, how can that be unless they are the same straight line? And T and T prime cannot be different because they lie on the same straight line, as Arjun points out. Okay, so this is nice. So this is sometimes very useful. This strategy is. Now we will move on a little bit to the next phase, which is a bit of involving transformation involving some tools that can be uh, attributed to complex numbers and vectors maybe sometimes. So the main idea is that if you want to prove that two things are equal, let's say there is an object called uh, maybe blue. You want that object to be equal to red, equal in some respect. Maybe they are equal in area, maybe they exactly fit into one another. One way to show that they exactly fit into one another, which is another way to say they are congruent, is by using some size preserving motion. If you can put the blue stuff on the red stuff, if you can place the blue stuff on the red stuff by some size or distance preserving motion, and this type of motion is sometimes called an isometry. If you can do that, if you can put the blue on the red, then that would be great, because then and you have to be convinced that you're putting it exactly on the red. You're putting it exactly on the red. So if that happens, then you would be able to say that the blue is exactly congruent to red. Now, some of the size preserving isometries or size preserving motions or isometries are reflection. Reflection changes the orientation but keeps the size and the distance the same. Rotation is an example. Rotation is another example. And then we have uh, translation. Translation it's quite an easy example, but a beautiful example nevertheless. But we will be speaking about a combination of rotation with another type of motion, which is not an isometry. Another motion which is not an isometry. This is called homothety. It basically does not preserve size. It is often known as a similarity transformation. So what does that mean? Well, I'm not going to go into the exact technical definition, but you can say that if it is for triangles, then the ratio of the sizes will be preserved. So for example, if you have a triangle ABC, one way to think about similarity transformation, homothety, is this, that you are simply blowing up each of the each of the points or the lengths by equal amounts. So it's like this. So one can prove a bunch of things about homotheties, and we will be focusing on a very specific one. So what we will do is, we will not only look at homothety, we will be looking at rotations with homothety, which is sometimes known as spiral similarities. Spiral similarity. Okay, so how are we going to do that? Okay, so okay, so more people are coming in. Why are they joining late? Getting confused now. Okay, so here is what I said in the last 2-3 minutes, so that the person who joined now will understand. I'm speaking about something called spiral similarity. It involves two other things: a rotation and a homothety. So what is rotation? Of course, I'm sure most of you know this. Rotation usually has a center point and a moving point. So you keep this OA fixed, the length of OA fixed, and if you move it, if you keep the point O fixed, if you sort of push OA, then whatever happens is rotation. This is A prime. So here is a strategy pointer, that whenever you are trying to use rotation, make sure that you hunt down the center of rotation. If you want to learn rotation, then you focus on the center of rotation. That is usually the easiest or the most useful thing. I wouldn't say easiest, but one of the most useful things. The second thing is the other transformation that I talked about a moment ago.
Sir, what does it mean to hunt down the center of rotation?
I mean, you have to figure out, let's not hunt, use the word hunt, figure out the center of rotation. If you suspect there is a rotation involved in the problem, and there are very good reasons why you might be able to trace it out with some experience, then one of the first things you would like to do is to find what is the center of rotation. That could be the clue to solving the rest of the problem. Okay, I'll give you examples what I mean by that. So this is one part of it. The other part of spiral similarity is homothety. I talked about it. Homothety is, in a minute ago I spoke what homothety is all about, but after that a couple of people joined, so I'll just quickly say, you can think of homothety as blowing up proportionally everything. So if you have a line segment AB like this, and if you are applying the transformation of homothety, and you can sort of blow it up like this, So this is A, let's call it CD. Okay, so AB he is here, CD is here. So you can say whatever amount of distance A has traveled, B has traveled proportionally. What do I even mean by that? What does it mean to say it has traveled proportionally? Well, in terms of exact arithmetic, it means that OC by OA is equal to OD by OC, OD by OB. And this is just for segments. You can do the same thing. You can do the same thing uh, for for triangles, for circles, for other geometric objects. You can blow them up. What we are studying here, however, is known as spiral similarity, which involves both rotation and homotheity, two things. So it's very important that you are able to imagine how you can think about it. It's very natural. It should come in your mind very naturally. What you do is you take a point. So let's say this is the center of rotation, and let's say this is point A. The way you should, that is rotating, but it is not only rotating, it is blowing up. It is not only rotating, it is blowing up, so it is getting larger in size as it rotates. I would strongly suggest that you not only focus on the end result of the motion, but you also focus on the motion itself, how it is moving. Okay, so this is OA. If you want to blow it up, it becomes like this, maybe. So A prime is here. So you got to think about how this all happened. You can slowly see the object rotating and all the time getting larger in size. So if it just rotated, it would have rotated like this. But didn't only rotate, it sort of got larger in size, right? So this is the key idea of spiral similarity. Okay, but now we are going to apply this to a very simple but powerful problem. This is a, you can think of this as the fundamental theorem of spiral similarity. Spiral similarity. Some sense? So what you're going to do is you will be showing that if you take a segment AB, let's say AB is 3 centimeter maybe, and you have another segment, let's say like this, MN. Let's say this is, I don't know, 1 centimeter. Okay, what you want to show is that these two objects are spirally similar. So AB is spirally similar to MN. Do you see how wonderful this theorem is? It says that you can take any segment and sort of rotate it about some point and shrink it and place it on any other segment. And this is very intuitive. You should be able to do this. Why? Because you can think of the line segment AB like this. It's kind of floating. It's moving on to MN and being shrunk to the size of MN. Isn't that possible? That's obviously that is possible. Why not? I mean, we can mentally think about it. AB is moving to MN all the time, shrinking to the size of MN. That is possible. Mentally, that is possible. That should be done. That should be doable using geometry. So, can you show rigorously that AB is spirally similar to MN? And to do that, the first thing you need to find out is the center of spiral similarity. So step one.
Uh, But sir, while we move AB, but we need to move AB such that it is rotating about a point. So
Exactly. So you need to show that there is a point. You don't know what point is that. That is what I precisely mean by hunt down the center of rotation. You have to figure out about what point this rotation is happening. And of course, then you have to check whether this shrinking is actually happening or not. So, can you, all of you, I'm giving you a little bit time, 2, 3, 4, 5 minutes, maybe a couple of minutes, find a center of rotation that works. Remember, when I say spiral similarity, I mean rotation and homotheity. The rotation and shrinking or expanding, whatever. So, the rotation part, let's take care of that first. Find the center of rotation that could work. And you know what? I'm going to tell you this: trust your imagination and instincts. Uh, Problems at a certain level are not won by simply knowing a bunch of theorems. You have to put your imagination into work. So forget about all the theorems that you know. Focus on the imagination. What is going on in the picture? Approximately where you should put the point of spiral similarity. Okay, I got a candidate here. Devansh Kamra is saying the ratio is preserved. Yes. The intersection of MB and AN. Okay. MB and AN. Let's join them. It's a very good suggestion, Devansh. Excellent suggestion. It's not totally right. It might not be right. In certain cases, it is right, but this is a good candidate. Okay, other person, Aryan Prakash, is saying maybe if we extend AB and MN and wherever they meet, maybe that point works. Okay, in certain situations, that could work, but I mean, it seems plausible. See how Aryan is thinking about it. Aryan is keeping his eyes here and he's thinking, okay, maybe this is swaying like this, right? Okay, that could be possible. What Devansh is thinking, okay, maybe it is like
Sir,
here, and
sir,
maybe you can just put it, rotate it like this, and place it like here. Okay, go ahead.
sir, we have to find the point such that every point on both the lines is equidistant to it.
Um, Not quite, because there will be a homotheity involved as well. So sizes will get distorted.
Yes, then
So
we will do the home trading.
okay,
Sir,
okay, yeah.
After
sir,
placing the equation.
Sorry, yeah.
sir, can I use the intersection of the perpendicular bisectors of AB and MN?
Okay, that's quite imaginative. Very nice. If you draw the perpendicular bisector of AB, if you draw the perpendicular bisector of MN, see how Ryan's brain is working. Ryan is thinking of this as a handle. He can sort of, I'm just guessing that's how he's thinking. That he's thinking that, okay, maybe he can sort of take it like this to here. And while he does that, this handle will be shrinking AB as well. Hmm, might work sometimes. Okay. So I'll just do one thing, since we are not in a geometric transformation class, this is just a review session. I don't have more time to sort of let you think. It's a sad thing because I should be giving you more time to think about it, and I'm sure you would get it yourself. I'll give you the candidate of the point, and you're going to prove that it indeed works. So what you do is you draw a circle through, let's say this point is T, the intersection point of the two triangles ATB and MTN, and then you say that, okay, look at this point O, the other point of intersection. Obviously, it could happen that there is no other point of intersection and the circles only intersect at the point T. That could also happen. Suppose if that happens, then your O is your T. That's fine. If that doesn't happen, that the other point O, this other point, is the center of spiral similarity. Okay. Try to formulate an argument why that should be true and tell me in a couple of minutes. I'll give you a couple of minutes to think about it. What would be an argument to actually make sure that indeed this happens?
So actually, we had a complex number module class, I think around 2 weeks back,
Okay.
in which I think some of us were there in that class also, and we covered all of this. So I am already familiar with that proof.
Okay. Did you use complex numbers to do this?
We did not. We used synthetic geometry to do this, but we spoke about spiral similarity as complex numbers.
Okay. Okay.
There's a big connection.
Sir, one thing to notice that angle AON is equal to angle BOM. So first we can rotate it and then we can do a homothety accordingly or something like that. Like it seems that we are in the right direction.
Okay. AOM.
No, AON.
Okay. AON. Okay. Let's exactly. Very nice. AON is equal to BON. BON. Okay. Why is that? Why?
Sir, because to prove that it suffices to show that angle MON is equal to angle AOB and angle MON is equal to angle MDN and angle AOB is equal to angle ATB, and those two angles are equal just by like vertically opposite angles. So we are
Okay. So what Arjun is saying is that this angle 1 here is equal to this angle 1 because of the stuff that is here, and this angle 2 here is equal to the angle 2 by the angle in the same segment property. Now this angle 1 and angle 2, they are equal to each other because of vertically opposite angle. So these two, all of these angles are equal. Okay. So if this angle is theta, then notice that angle BOM is 1 plus theta and angle AON is 1 plus theta. So this angle right here is equal to this angle. Okay, fine. These two angles are equal. So it is plausible that OA rotates to ON, OA rotates to ON, and OB rotates to OM simultaneously because both of those angles are equal. Okay, how would you show that it is indeed a spiral similarity? Okay, what you do is
sir,
go ahead.
the thing I think is that I don't know whether it is true or not. Like consider a point, say L on line OA says that OL is equal to ON.
Sorry.
Consider a point L on line OA such that length of segment OL is equal to length of segment ON.
Okay. Uh,
Maybe a point P and Q on ON and OB.
I think it is much simpler than that. You don't have
So
to.
could we also think of it as if you rotate the entire triangle OAB using O as the center of rotation, and so OA will coincide with ON and OB with OM, and then we use homothety, it will give us triangle OMN.
But for that you need to show that the line will be parallel, that the reflection of that the point where A get mapped to and the point where B get mapped to, the line joining those two lines will be parallel to MN.
So, but we showed that AOB is same as MON, right? They're both one.
AOB, yeah. No, I'm saying
OA will be ON, right?
OA would be on OM, yes.
Yes, like it will be longer than that, and OB will be on, like OM will be on OB, and then we use homothety.
But these two lines may not be parallel.
Oh, yes.
So yeah, that's a good idea actually. So if you could show that OA over ON because OA rotates to ON, right? So OA over ON, the amount of shrinkage of OA should be equal to the amount of shrinkage of OB.
Yeah, sir, we can easily prove this. This is just by similar triangles. We have already proved that angle AON is equal to angle MOB, and also we see that angle ANO is equal to angle BMO. So by AA criteria of congruence, we can conclude that triangle AON is similar to triangle BOM. So we get our desired result.
Okay, yeah, of course. So what um, Arjun is saying is that this red angle, sorry, this red angle is already proven to be equal with this green angle. Now we have also shown, also this angle is equal to this one. So if this is angle 1, then this is angle 1, or maybe I can call it 2. And if this is angle 3, then this is also angle 3. So in this picture, now we have BMO similar to ANO. So we can get this particular ratio for our purpose. So this is good. This is fine. Now, Gautam told me that you have already sort of learned this. So some of you, maybe not all of you. So what we are going to do is we will be using this and some other tools to move on to the application. So suppose we have a cyclic quadrilateral AB.
Sir,
Sorry.
sir, I just wanted to ask why the perpendicular bisectors thing would not work. Just like an example where it would not work.
Oh, why would it not work? Okay, so if you join O to the uh, midpoint of AB, if O has to be
But
the,
in which case will it work? Like, how can we get like? Why do you think it will work?
I mean, you could create a case, Ryan, where it wouldn't work because what you would say essentially is that if you join O with the midpoint M of AB, that is passing through the center. That's what you're claiming, right? This
Yeah.
O prime, because only then O prime M will be perpendicular to this, right? But if you have two arbitrary circles, you can arrange for this point to not, like if you have a point like this, it may not pass through the midpoint. I mean the center may not be on the midpoint, on the line connecting O with the midpoint of that particular chord.
Sir, does the shrinking to be done must be done in tandem with the rotation, or can we do it after?
It should be done simultaneously with the rotation, but it doesn't
Okay,
really
sir. Then
matter because if you do the shrinking first and then the rotation, or if you do the rotation first and then the shrinking, both should yield the same result. I would say you should imagine that they are done together, because in more stricter terms, that these two operations are commutative, so it doesn't matter which one you do first.
sir, then I would say that mine is correct because after we rotate the perpendicular bisectors, after we rotate that, it comes out both lines AB and MN become parallel, right?
I don't know. Okay, let's see.
Even if they become parallel, then you need to show that like the respective points are collinear with O, like the lines meet at O. Like
So
only
okay,
parallel wouldn't imply existence of a homotheties.
if you have these two, okay, okay, let's see. If you have these two like this, so what is the angle of rotation, Ryan?
Until the two perpendicular bisectors coincide, that is the angle of rotation.
Okay, so you are saying that MON is the angle of rotation. Is that what you're saying?
Yes, sir.
Okay, so let's do that. They are,
But I think your method will work only if angle AOB is equal to angle COD. So that's not always true.
I'm coming to that.
okay, fine.
Uh,
Because ultimately, if you need homothety, as Arjun is pointing out, you would need, oops, what is happening here? Yeah, you would need, wait, here we go. You would need OCA to be on the same straight line, which might not happen.
yes, sir. I know that might not happen, but I am simply saying that we should connect A and we should draw the line AC and BD and then connect them to O dash and then straight by that method. I'm not.
I understand what you're saying. Yeah, that would work actually, but the thing is, Ryan, when we say center of spiral similarity, you would want the same center to work for both the rotation and the shrinking. So you are right in that sense. If we are allowed to choose two different points, one for rotation, one for spiral homothety, then your method definitely works. But if you want the 2 points to be the same point, then then you would need this. Okay. Okay.
Thank you, sir.
Okay, very nice. All right, so let's go toward the application. We are getting closer to the end of this session, so we should. How long are these sessions? How long was the session for yesterday? I don't know.
Around 1.5 hours.
Okay, okay. So we have this ABCD is a cyclic quadrilateral. Oops, sorry, 1.5 hours to do. Okay. So okay, so then we have some time. So we have this circle. Let's say let's go like this. This is the, let's draw a circle. Let's draw a cyclic quadrilateral ABCD. Maybe I can draw it a little bit smaller. Maybe I don't know. Maybe I can draw it a little bit smaller because I'll need more space. So I'll just, okay. Oh, clear all content. Oh, what happened? Anyway, so let's draw it a little bit more smaller. So you have a cyclic quadrilateral ABCD, A, B, C, and D. Okay, and what you want to do is we want to extend the line AB and CD to meet at some point T. So here, okay. So this is exactly what I feared. Just bring it down a little bit. Okay, and we are going to extend the other two as well. So sort of moving toward the Meikle point consideration configuration, if you know what that is. If you don't know, that is also fine. So this is T, this is S. So I'm just extending. By the way, I think I have taken a seminar before on Meikle point configuration. How many of you attended that? Do any of you know what is the Meikle point configuration?
Sir, I know the Mickle point theorem and it converges that like those three circles intersect at a common point, but I am not sure which configuration you're talking about.
Okay, fine. So anyway, we'll see. So we have this T and S. These are the three, the 2 points where the extended lines meet, and the lines. Uh, Now we have a Meikle point of the quadrilateral ABCD. So let's call that point by some name. Let's Meikle point is M. So let's call it M. So if you do not know what that is, okay, so maybe I have to say a little bit about it. So let me just quickly say what it is. So you basically, there is a very beautiful set of circles that you can draw here. What you can do is you can draw the circle TCB. So, okay, quickly draw this circle, draw this circle, draw this circle, and draw this circle. Okay, so 4 circles. Can you quickly draw them in your notebook? Maybe like this. One, okay, two. As soon as you draw two of them, you got the equal point, which is the point right here. M, right? And what you can show essentially is that this one, TDA, this circle, this point, this particular green circle passes through the point M. Can you guys quickly prove that? I'll give you a minute to think about it. It's not hard, it's quite easy actually. And this is a very popular theorem in geometry. Maybe you have seen it before. If you have not, that's all right as well. Go ahead and prove that M.
Yes, sir. It's just angle chasing. We can prove that the sum of opposite angles sums to 180 degree.
Okay, that's right. So I'm not going to give you a lot of time on this because this particular problem, I mean, okay, I'll give you a couple of minutes time. Don't get me wrong. This is just a review class for INMO. In a normal geometry class, I would spend a little bit more time on that. But since this is just a review class for the INMO students, cannot spend a lot. So essentially what you want to show is that TMAD is a cyclic quadrilateral. TMAD is a cyclic quadrilateral. Go ahead and try to show that TMAD is a cyclic quadrilateral. I'll give you a minute for the people who have not seen this before. TMAD is cyclic. Why? So maybe a couple of minutes time for that. So as June rightly pointed out, this is just angle chasing. You don't need to worry too much. Okay, so I'm not going to give you more time. Arjun, can you tell me how to show that this is true?
So since points T, C, B, M lie on a circle, in fact that quadrilateral is cyclic, so angle
TC
TMB will be equal to angle uh, SCD
TMB, like this angle right here,
is equal to SCD.
is equal to SCD. Okay, so this angle right here,
Yeah.
because exterior angle of a
Uh,
cyclic quadrilateral is equal to the interior opposite angle. Okay.
yeah. And also we know that angle SM sorry, angle BMA is equal to angle BSA.
BMA, which is this angle right here, is equal to angle BSA because this is a circle. This is a circle and they are
Um,
subtended by the same chord. So yeah, okay.
Now just to mark the angle CDS in some other color.
Okay,
Uh,
CDS. This angle is suppose golden or
Yeah.
yellow. Okay.
If we look at triangle CDS, we know that the sum of red, blue, and golden is 180 degree. So now, if we look at quadrilateral TDAM, angle TDA is just the golden angle, and angle TMA is angle blue, red plus blue. So this means that the sum of opposite angles of quadrilateral TDAM is 180 degree, which shows
Excellent.
that quadrilateral is cyclic.
Excellent. So basically what happens is these three angles is 180, and these two angles right here are basically these two angles. So these three angles would be also 180. That means the opposite angles would add up to 180. So this is fine. Okay, so the green one works exactly by the same logic. The This one would be true. So the golden circle. So you have four circles passing through the same point M, which is awesome, I think. Okay, so now can you show, now that now that you got a grip on this, can you show that TMS is like collinear? TMS is collinear, are collinear rather, collinear. So you can just join TMS like this by a single straight line.
Yes, sir. This also follows that because we can just show that angle AMS with the normal angle chasing is equal to the golden angle, which
AMS is equal to the golden angle. Why?
because the golden angle is equal to ABS and ABS is equal to AMS because of the cyclicity. So that's why.
Acha, AMS is equal to, so I'll just mark what he's saying. This angle right here is equal to this angle right here because
And
this
those
is
red and marked angle, that red marked angle is equal to the golden angle
this is equal to the golden angle.
because quadrilateral ABCD is cyclic. Yeah.
Exactly, exactly. So this is terrific. So we have this, we have this, so we have the desired effect. So these three, golden, blue, and red angle together is 180 degree, and we have a simple beautiful straight line, TMS. Excellent. So that is not exactly our problem. Our problem is basically about, so we were trying to learn about spiral similarity, remember, a moment ago. So we are going to relate the Meikle point with the spiral similarity. So the Meikle point is a point which is the center of spiral similarity related to the triangle ABCD. So here is the claim. Here is the claim. Claim is that M is the center of spiral similarity. spiral similarity that sends AB to DC. AB goes to DC, that means A goes to D and B goes to C. And it also sends AD to BC. So A goes to B and D goes to C. So both of you can visualize the same thing in two ways. So I'm going to tell you one thing before I go here. If you come back to this picture, there are two ways of thinking about it. So I'll just mark them a little bit differently. So what I'll do is I'll just put it, okay. So I will be, I'll just borrow the names from the other one. So here the name is AB and DC. Okay. So I'm just going to do that. So A goes to D and B goes to C. Okay. Now our picture is kind of like that. So if you look at it, if you take the center of spiral similarity O, this is something you have to think, that OA is sent to OD. OA is sent to OD and OB rotates to OC. OB rotates to OC, which basically means, if think about these two letters, AB is sent to DC, A goes to D, B goes to C, right? That's what's going on. A goes to D and B goes to C, right? But there is another thing that you can think of it, another way you can think of it, another type of spiral similarity that is also happening here, and that is, you can think of this as, okay, what was the letters here? A goes to D, B goes to C, exactly same thing is happening here. And we
Sir,
could say,
one another thing which I think is that the two centers of spiral similarity should exist, because in this figure we have like AD and BC lines are intersecting, but it might happen that lines AC and BD intersect. So we can like get two centers of spiral similarity according to me.
okay, so this is the other one in some sense. Here A goes to B, A goes to B and D goes to C with respect to the same center. Why is that? Well, how can you show that this is happening? A goes to B and D goes to C. So essentially AC is being sent to BD.
Sir, because the triangles C and triangle AO is similar. As we proved earlier.
So AOB is similar to COD, right? Is that right? Is that what you're saying?
No, sir. I said that AOD is similar to BOC.
AOD is similar to BOC. Okay, yeah, of course.
So it means that AO by BO is equal to DO by CO.
AO by BO is equal to DO by CO. Yes.
So that proves one part. Another part is similar because their angles, we know that their angles, like we proved earlier, the same angle of rotation. So
Perfect.
done, right?
Exactly. So what you are saying is that if you, so you have to think of this particular rotation in this way. So if you are looking at this rotation, how would you imagine this? You are imagining it OA moving to this particular position. So in this direction, sorry, in this direction. OA is closing on like this. At the same time, OC is closing on like this. So this entire line is getting floated about this point to here. And while it happens, it is getting shrunk to BD. So AD is going to BC. AD is this particular line right here, and BC is this particular line right here. So this crisscrossing lines are also getting sort of squished together. This is perhaps the most important part of spiral similarity, that two spiral similarities happen simultaneously. One is the two exterior ones, AB and CD. AB and CD. One of them are not intersected. One of them is standing outside like this. Okay. The other one is the crisscrossed line. So this is AD getting spirally pushed to BC. So if you think about it naively, you would think that T would be the center of that particular rotation. That would happen if T was the midpoint of AD and BC, right? That would happen. You could just move like this, like this. You could move like this, A to B and B to C. Unfortunately, T is not the midpoint of AB. I mean, it might not be the midpoint of AD. So in that case, we have to use this other point. So I'll draw a picture. This is perhaps the most important part of what you are learning today, because this is literally what we'll be using, and hopefully, oh, what happened there? Okay. I'll just share the board one more time. Okay, so here we go. So what I'm saying here is that you have to focus on two pieces. One is ABCD, and then you have to also, so this is like flowing like this about O. And the other thing that you have to focus on is AD squishing into, turning into BC. AD turning into BC. There are two things happening here, okay? And both of them are pretty simple to understand once you think about it. Okay, so if you look at the Mickle point problem, the Mickle point of a quadrilateral, a cyclic quadrilateral ABCD, then the claim was that M is the center of spiral similarity that takes AB to DC and AD to BC. So how can you quickly argue it? Can anyone tell me quickly why that is obviously true?
What do we need to prove? Like M takes which line to which one?
So M takes AB to DC and AD to BC. AB to DC and AD to BC.
So just sort of like a first instinct type thing for me would be to try to do the same construction that we did for finding the center of spiral similarity on the previous slide, one or two slides ago, and do the same thing and do it for both the spiral similarities that we want to look at. And then I think we will end up with constructing the Mickle point, and so they will be the same.
Okay, so what you are suggesting is just do AD and sorry, what is this, BD, and if you want, okay, so the one is AB to DC, so AB to DC. So we want to sort of join these two and then take the two circles. Okay, that is what Gautam is suggesting, maybe. Is that what you're
yes, I was suggesting that, but now I'm not so sure if it will work.
Okay. So I'll draw a
Sir,
cleaner
haven't we just constructed the point of similarity? Like, can you go to the previous picture where the figure is drawn?
Okay. So okay, I'll just do it, but I'll just
Uh,
draw it in a more cleaner way. Okay, just to make sure that everyone is on the same page and no one is getting confused. So you have A, B. Okay, first I'll draw the circle. So you have a circle like this. This is sort of the first circle in the picture of many circles that we have here. So you have A, B, C, D. Here is A. We have B. And we have C. We have D. Let's join this. So CD. Okay. So I would like to show that the Meikle point of this particular quadrilateral, actually the way I have drawn it, it would be tremendously large picture. So I'll just adjust it a little bit more. Yeah. So that they, if I extend them, this kind of meet close to the big circle, so that I don't have to draw weird pictures. Okay, so this is the cyclic quadrilateral, and we want to show that the Meikle point M is the center of spiral similarity that sends AB to DC and sends AD to BC simultaneously. You can think of it in two ways. Okay, now I'll go to the board that Arjun has asked me to. Which board should I go to, Arjun?
Sir, on the board where you have made those circles and that figure, that big figure.
Okay, here we go.
Yeah, yeah. So, sir, basically, let's look at line AB and DC. Like we have just constructed its Mickle, these two lines intersect at point T, and basically the circumcircle of triangle TBC and TAD intersect at point M. Like we had shown that M lies on circumcircle of triangle ADC. Oh, sorry, ADT. So basically, we have just constructed it. So we are
Precisely,
done.
precisely, precisely. So what uh, Arjun is suggesting is that basically we constructed the center of spiral similarity indirectly. What did we do? We just had to construct the two. First, we made them intersect, and then we have to construct the intersection point of intersection. We have to take the point of intersection of the two circles. So let's see if that is exactly what's happening here a little bit more, because this is not intersecting inside the quadrilateral, it is intersecting outside, so it might confuse some of you. I'll be just drawing it one more time just to make sure that we all understand from the scratch that this is indeed happening. So we have this one circle and we have this sort of the other circle, and my mission will fail because I'm not using enough colors, so I'll just use a little bit more colors. Okay.
Sir, just one thing I want to ask you, while drawing, suppose our final diagram in more, maybe while practicing also, do you think it is nice to draw the figure with say color, different color with color pencil, or it doesn't really matter much if you draw it by scale and ruler,
Yeah, it doesn't
etc.
really matter. Yeah. As long as you have a neat and clean picture, that's fine. I mean, sometimes sometimes using color codes can make things easier for you. So I can suggest one thing that has worked previously for other students. Make extensive rough notes and use all those red, blue names and colors when you use that. Sometimes the grader will first look into, if the rough notes are really good, the grader will look into that first. So, and if the main idea is correct there, the job of the grader becomes very easy. Okay, so M. Okay.
Sir, I didn't get you. In when I last did give RMO, they also asked us to give our rough sheets.
Exactly.
But I think the purpose of rough sheets is only to check that you have not cheated from anyone.
No, 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 no.
But do they also see the rough sheets
They
or
do see yeah, of course. They, remember exactly the point, Arjun. They asked you to give the rough sheets, right? So one of the things what I would suggest you could do is split your page into two more or less same portions and make this the fair and make this the rough. And then here in the rough, you more or less use color codes, you use names like red, blue, green, yellow, whatever. You can write red is equal to the red. You could use solid red is equal to the to the not solid red. And it's about communication, right? Colors can be used interestingly to do communication. So instead of writing angle ACD is equal to angle KC is equal to angle uh, BTY, I mean obscure stuff like that, which you should write in the fair part, write it here. But red, solid red, not solid red, those things you write on the rough side. So that could be useful. If you are not in a habit of doing that, I don't suggest starting at INMO. If you are not in a habit of doing that, but yeah, this is something you can think about. Okay, all right. So yeah, now coming back to it, we I think we're just in the closing part. So M takes A to D, A sorry, A AB to DC. That's what we want to show. A to D, B to C. Why? Because if you join AM, MA, and MD, and MB, and MC, you can precisely show that to be true. How can you show that? Can you manually show that to be true in this particular picture?
Yeah, sir.
Okay.
The first thing we notice that angle AMD is equal to angle ATD is equal to angle BTC is equal to angle BMC.
Okay.
So this just shows that angle AMB is equal to angle BMC. So that angle thing
Okay.
is fine.
First, let me say AMD. That's what you're saying, right? AMD
Yeah.
is equals to angle BMC. Why
Yeah.
would that be important? Because you want this rotation to be equal to this rotation. So
Yeah. So now it's only left to prove that the ratios are also equal. Like we want to prove that MA by MD is equal to MB by MC.
MA by MD is equal to MB by MC. How would you prove that?
Just a second.
Yeah, take your
This
time.
seems almost done.
I mean, you can guess how would you do it. You will just use similar triangles for this.
Yeah. This is. Sir, I can say that ADM is equal to ATM.
Yeah, ADM, this angle is equals to ATM, this angle,
which is equal to BCM.
which is equal to BCM, which is this angle.
We know that BMA.
BM, BMA, okay.
Delhi, Mumbai, Allahabad.
Oh, Delhi, Mumbai, Allahabad. Okay, so this angle
is equal to this the DTA.
DTA, yes.
Which is again equal to BTC, which is equal to BMC.
BMC, okay.
Similarity proved.
Okay, excellent. So what Ryan just showed is that triangle ADM is similar to triangle BMC, which sort of does our job, right? Because then we have MB by MC is equal to MA by MD, and you are convinced now that this is indeed the center of spiral similarity that takes AB to CD, the AB to DC. The only thing that remains to be sort of imagined, and I cannot stress this more, that you have to use your imagination. Otherwise, if you just think of this as another theorem, you'd be totally missing the point. So I would want you to imagine how AB floats to DC, and this is sort of the tracker path. AB is floating to DC. You see?
Sir, are you aware of some like a presentation? Like there are some generally some presentation which like shows a path how it can float to that one. Like there are some presentation how net folds to a solid cube. So maybe if we can see those presentation, it will be easy to us to visualize
Yeah, of
what is
course.
happening exactly.
Yeah, definitely. You could do that. I would suggest though, there is another hardware that you can use for doing this. Can you guess what that hardware is, Arjun?
GeoGebra.
Hardware.
Oh.
It's right here.
Oh, your brain.
Yeah.
Okay.
But you're right. You're right. We can use the softwares to definitely make our life a much easier. But you're right, Arjun. We can use that. Okay. So now coming back to this, we see how AB is floating to AD is AB is floating to AD. I'm sorry, DC. AB is floating to DC. We see that AB is floating to DC. How is AD floating to BC? AD, how is it floating to BC?
Sir, just a quick question.
Yes.
I may have gotten this wrong, but here it looks like so we've taken it looks like we're rotating triangle MCB and then sort of like aligning it with AD and then applying the homothéty from M. So it looks like we're mapping BC to AD.
We are mapping BC. Sorry, maybe you're right. Let me see. BC to AB. What? Sorry, BC to AD. That's what you're saying?
Yes. BC to AD.
BC to AD. BC to AD. Okay. You got right, I think. C is going to BC to AD. Yeah, exactly. That's what I'm saying. The next thing that I'm saying is this, that BC to AD. Why? Because this is the other flow line that you should be thinking about.
No, sir. What I asked is, it looks like what we just proved, the exact configuration that we just proved is AD to BC, not AB to CD or AB to DC.
You said, okay, so you're saying this is not what we proved. We proved this one.
That's what it seems like to me.
Okay, it might be true. I think you were right. Maybe I'm just. Let me just think about it. Okay, maybe you're right. So this is AD to BC, AD to BC, So definitely C is going to okay.
But sir, the key thing is that we are not rotating point D anywhere. So how can AD go to BC? Like we are rotating points A and B. So AB must go to something, which I think.
AB must go to something. Yeah,
but Arjun, my understanding is that so we proved that BMC is equal to AMD, right? Which suggests that we are rotating BMC to fit on top of AMD and then applying homothéty.
Okay. Yeah, I think so this triangle is going to this triangle. That's what Gotham is saying, right? That's what he's saying, right?
Yes.
So what I think about is that like the equality of angles AMD and BMC is not just that these two angles are equal. It also gives that angle AMB is equal to angle DMC. So basically, like we are getting two things at a time.
Yeah, but then
what I think.
yeah, but yeah, absolutely. But then basically then we have to look at this triangle, moving to this triangle.
And that is what either we approved or we are about to prove.
Yeah, then we will get the top one. Gautam is right. And but the one that we just showed, which is basically this piece going to this piece, this is the other one, that is BC AD going to BC, this one. Okay, okay, that's great. So we have both of these pieces together. So M is going to M is the center of spiral similarity. I'm just going to wrap up this session with one pointer that might give you a clue why this would be very useful. If you take, if there is a spiral similarity between two objects, there are not many points that are under your control, but there are some points, some ways, some things that are under your control. For example, the midpoint is under your control. You can tell that the midpoint of one segment goes exactly to the midpoint of the other segment because it is proportionally shrunk or expanded. Do all of you understand what I'm saying here? If you proportionally increase one piece to the other piece, then the midpoint of this one will go to the midpoint of the other one. If you take a point which is 1/3 away from point A, it will go to a point which is 1/3 away to the target of the point A.
Yes, sir. So I think we can use this to obtain that two angles are equal, which I think may not seem trivial.
Exactly. So, for example, you could say that you could say that the midpoint of okay, the midpoint of A B goes to the midpoint of DC, right? And you could also say, sorry, go ahead, Arjun, you're saying something.
Yeah, sir. I'm saying this is a very nice thing because we can equate angles and ratios together. This also gives that MA the if we mark AB midpoint CD as x and y respectively, then this would also give that MX by MY is equal to MA by MD. So we are on and we can also get relation in angles. That angle XMY is equal to AMD. So it's very nice.
It is excellent. It is very nice. It is very nice. So this is good. This is good. So I'll just wrap up today's session by going back to the application problem once that we have here. So M is certainly the Mickel point of this particular quadrilateral. Now we want to show that this OM, if you draw O as the center of the cyclic quadrilateral that you started with, this is O and this is M. OM, you want to show that OM is perpendicular to TS. But wait, you don't want to show this using, let's say, all sorts of angle chasing or whatever. You want to show this using this spiral similarity technique. So how would you do that? Well, you focus on the midpoints of AB and DC. So you take the midpoint of AB, you take the midpoint of DC. Suppose this is what, G and H maybe. I hope there is no H in the picture. Okay. So can anyone tell me what is the relationship of OG with OH? OG with AB. OG and AB. Can anyone tell me what is the relation between them?
Sir, those two lines are perpendicular.
They have to be perpendicular, right? Because it's a chord This is the center. You just join the midpoint of the chord to the center. Okay, same thing. OH is perpendicular to CD. So G is sent to H, correct? Do all of you agree with that? G is sent to H by the spiral similarity, right? As AB goes to DC, G goes to H, right? Okay, so if you look at this M, point M, then this is A going to G, A going to D. I'll write it down. A going to D and G going to H. Just focus on this much information. Just put it here. Focus.
Sir, I think this gives us that angle AMD is equal to angle GMH.
Very good. Something like that, definitely. So use just the spiral similarity to finish the proof of OM being perpendicular to TS. Don't use angle chasing because that will defeat the cause that we are fighting for. To understand and use spiral similarity, and all the time, well, we're not only learning spiral similarity, we are using a bunch of applications here, but if you are able to show that OM is perpendicular to TS, then, well, then you have a very good application for this particular technique. Okay, now I am going to stop the session for today. I don't know when Srijit has put my next session, but I will definitely meet you guys next time. Okay, till then, bye.
Sir, will we be discussing this problem in the next session, or will we be discussing this on the group, or should we send a solution on group heads?
You should send the solution in group. I will also discuss part of it in the next session if all of you did not get this final solution. Okay, and then we will move on to some more beautiful ideas in geometry. Okay. Yes, Aryan, did you say something?
Sir, when you were explaining, starting with the center of spiral similarity, so you use the intersection point of the two alternate, like one, like B going to B and A going to C, and then you drew the circle. Right. But sir, like in the next problem, when you use P, sir, you use B, C, and A, B. So is it okay for both, or does it only hold for the crosses?
I mean, you get two types of. You get two sort of two different Mickle points depending on what point you will want to send to which point.
Oh, okay, sir.
It depends on which. Yeah, you're right, Aryan. This point is needs a bit attention. So what Aryan is saying, once we did a crisscross, once we just extended it and then did it. So yes, which one to use when? Well, it depends. That's the flexibility part. It depends on what point you are wanting to send to what point. So this is an exercise. It's a very good exercise that all of you can do. Draw two segments and see if you want to send this one to this one and this one to this one, where should be the spiral similarity center. If you want to send corner wise, where should be the spiral similarity center. Okay, so try to convince yourself which construction to which use at what point, and I think you will see through it. Okay.
Sir, one last question.
Yeah, sure.
Is there any that there are only two or less centers of spiral symmetry?
There are only what? Sorry.
There is there any proof that there are two or less centers of spiral symmetry, the spiral similarity?
Oh, so you see, given that there are, if you're looking at this configuration, you want A to go to one of the 3 points, B, C, or
no,
D.
Sir, he's asking that we have constructed two centers of spiral similarity. So he's asking that can we construct more? If no, then can we prove that we cannot construct more?
Yeah, I'm just saying that. Yeah, I understand his question. So if you look at the places where A can go, A can go to B, A can go to C, A can go to D, right? There are only 3 places A can go, given the 2 segments, AB and DC. The question is, if the 2 points of spiral similarity that you constructed gives you all these visits, that can be used to show that there aren't any more. So I don't know whether that answers your question.
So, sir, according to you, there are only 3 centers of spiral similarity. Suppose we want to map line AB to DC or even segment. So, can we show that there is a unique point mapping point A to D and B to C or those segments?
Yeah, there is a unique point mapping, making that map happen. Yes.
For example, can also prove it rigorously.
Yeah, you can prove it rigorously. Just first create the one point which works, and then put another invisible point and claim that that also works, and show that the angle or the ratios fail.
Actually, I think in our construction at that point, I think all of them were if and only if statements. Right. I think all of them are reversible. So.
Right. Okay. Bye. Take care, all of you. Bye.
Thank you for the class, sir.
Thank you, sir.
Thank you.